All right, if you're getting ready for the UPSC prelims, you already know that plate tectonics is a topic you just can't skip. It's absolutely foundational. So in this explainer, we're going to break down everything you need to know to walk into that exam and absolutely nail those questions. Let's dive right in.
Okay, I want you to really lock this sentence in. Seriously. Think of it as the master key to this entire topic. Everything we're going to talk about today, every mountain range, every volcano, every single earthquake, it all traces back to this one powerful idea. You get this chain of command, and trust me, you are already halfway to mastering this. So, let's start with a big question. How on earth do we actually know what's thousands of kilometers down, deep inside our planet? I mean, it's not like we've drilled down to the core, right? The answer is pretty ingenious. We listen. We listen to the echoes of earthquakes, these powerful vibrations called seismic waves that travel right through the Earth. Now, to figure this out, you've got to meet the two main characters in this story, P waves and S waves. So P waves, or primary waves, are kind of like the all-access pass. They push and pull like a sound wave, and they can travel through pretty much anything, solids, liquids, and gases. But then you have the S waves, the secondary waves, and these guys are much, much pickier. They move side to side in a wiggle, and they can only travel through solids. And that one little difference, well, that's the key to unlocking the Earth's biggest secret. And this right here, this is the big aha moment. You see, when scientists started tracking these waves from earthquakes, they noticed something incredible. The P waves would travel right through the center of the Earth and come out the other side. But the S waves, they'd get to a certain point, the outer core, and they would just vanish. They'd stop dead in their tracks. And since we know S waves can't travel through liquids, the conclusion was just unavoidable. Earth's outer core has to be liquid. It's just an amazing piece of scientific detective work, isn't it? Okay, so now that we have the evidence, we can actually map out the Earth's structure. Let's build on that and look at the layers themselves. We're going to see how they all fit together to create this incredibly dynamic system, and we'll start right from the surface and work our way down. First up, we've got the lithosphere. Now, it's really important to get this right. The lithosphere isn't just the crust we walk on, it's the crust and that solid, rigid uppermost bit of the mantle, all fused together. And here's the kicker. It's not one single piece. It's shattered, broken into these enormous, rigid slabs. These are the tectonic plates we're always talking about. This is the stage where all the action happens. Now, directly underneath that rigid lithosphere, you find the real game changer, the asthenosphere. This is the layer that makes everything possible. The key thing to remember here is that it's not a solid, but it's not a liquid either. The best way to think about it is like a super hot, really soft, gooey plastic. And because it can flow ever so slowly, it lets those huge, heavy lithospheric plates kind of float and drift around on top of it. Honestly, without the asthenosphere, there would be no plate tectonics, period. So let's just quickly recap. We know what's moving. Those are the lithospheric plates. And we know how they're able to move. They're floating on that soft asthenosphere. But that brings us to the biggest question of all. Why are they moving? What's the engine that's actually driving this whole planetary machine? Well, the engine is something called convection. And you've seen this happen before, every time you boil a pot of water. Hot, less dense material deep inside the Earth's mantle gets heated up, and it rises. When it gets near the surface, it spreads out and cools down, which makes it denser. And what does dense stuff do? It sinks. This creates a giant, circular, slow-motion loop. And the lithospheric plates? They're just sitting on top, getting dragged along for the ride like they're on a massive planetary conveyor belt. Okay, pay close attention now, because this is where everything really clicks, especially for your exam. We've got these plates moving around, so what happens when they run into each other, when they pull apart, or when they just grind past one another? Well, that's where all the action is. We're talking mountains, volcanoes, earthquakes, the whole shebang. Let's break down what happens at these plate boundaries. So, there are three main types of boundaries you absolutely have to know. First, you have convergent boundaries. This is where plates collide head-on. All that pressure has to go somewhere, so it pushes the land up to form massive mountains, like the Himalayas. Then you have divergent boundaries, where plates are pulling apart. This allows magma from the mantle to ooze up and create new crust, which is exactly what's happening at the Mid-Atlantic Ridge. And finally, you have transform boundaries. This is where plates slide sideways past each other, building up tons of stress that eventually gets released in, you guessed it, massive earthquakes. The San Andreas Fault in California is the classic example. But let's just zoom in on those convergent boundaries for a second, because there's a little more to the story. They're not all the same, you see. If two continental plates smash into each other, Neither one wants to give way, so they just buckle and crumple up, creating enormous mountain ranges. But what if a dense, heavy oceanic plate collides with a lighter continental plate? Well, the oceanic plate loses that fight. It gets forced to dive down underneath the continent. That process is called subduction, and it's what creates fiery volcanoes and super deep ocean trenches. So remember, the type of crust involved completely changes the result. Wow, okay, we've journeyed from the very core of the Earth all the way up to the crust. We've talked about seismic waves, and we've talked about mountain ranges. So now let's put it all together. Let's connect all these dots and see how this incredible system explains the very world you and I see around us every day. And if you want to see this whole theory play out in the real world, look no further than the Pacific Ring of Fire. It's this huge horseshoe-shaped belt that wraps all the way around the Pacific Ocean. And what's happening there? You have multiple plates crashing into each other, subducting and grinding past one another. The result is just staggering. This one area is home to over 75% of the world's active volcanoes and something like 90% of all earthquakes. That pattern isn't just a coincidence. It is a direct, predictable consequence of plate tectonics in action. So let's just recap that entire chain of command one more time, from the inside out. It all starts with the liquid outer core, which generates heat. That heat drives those massive convection currents in the mantle. Those currents act like a conveyor belt for the rigid lithospheric plates. And how can those plates move? Because they're floating on that soft plastic asthenosphere. And finally, all that movement leads to action at the plate boundaries, which is what creates all the mountains, volcanoes, and earthquakes that shape the face of our planet. See? It all connects. All right, to wrap things up, let's put your knowledge to the test with a question that's exactly like something you might see on the prelims. The existence of the asthenosphere is critical for plate tectonics primarily because it is. Now think about it. Is it A, B, C, or D? We've talked about this. It's that special layer that lets the plates move. The answer, of course, is C. It's a plastic flowing layer. If you got that, you've really understood the fundamental logic we've been talking about. Just remember that chain of command from the core to the crust, and you are going to be in great shape for your exam.